All right, we're back. We did section 3.2 yesterday on the mean value theorem. We didn't quite get through it all. So I think I'm going to do a couple more examples using that theorem. So we'll finish that up this video, and then I'll do another video or two on the next section. So here we go. Continuing section 3.2, excuse me. I'll just make a note there. This is continuing section 3.2. Okay. And I'm going to rewrite this function because obviously the equation feature didn't work. If I have the equation f of x is equal to 2 times x to the 1/3 power, and then we're considering that on the interval -8 to 8. We did a problem yesterday, just like this, and the goal to this is I want to first verify that all the conditions of the mean value theorem are satisfied. So I want to verify that all conditions of, often it is abbreviated the MVT, mean value theorem, are satisfied. And if they are, let's find the value of C. And if so, let's find C that satisfies the conclusion. Satisfies the conclusion. Okay, so I'm given a function f. I first of all need to figure out, are all the conditions satisfied? So first condition is I have to verify that this is continuous on the closed interval that we're given. I've already said that x to the 1/3 is continuous everywhere, is continuous on -infinity to infinity. So that means 2x to the 1/3 is as well. So it is continuous certainly on a portion of the real number line, because it's continuous on all of the real number line. Now I want to check, is it defined, is it continuous on a closed interval? We're given this closed interval -8 to 8, which is closed. So I've got that part. And then finally, I need to check and make sure that the derivative exists on that interval, -8 to 8, which means I need to find the derivative. F prime of x is equal to 2 times 1/3 x to the 1/3 minus 1, which is -2/3, which I could rewrite as 2 divided by 3 x to the 2/3 power, because I have a negative exponent here. I can rewrite it with x in the denominator. And now we see we have a problem for this. Note that the denominator could possibly be 0. Note that if 3x to the 2/3 equals 0, the derivative f prime does not exist. Does not exist. Okay, so I've got that. That obviously happens when x equals 0, which happens to be in the interval from -8 to 8. So the condition, the final condition for the mean value theorem is not satisfied. Let's see, let's clear that. So f prime of x does not exist for x equals 0 in the interval -8 to 8. So I can't apply the mean value theorem. I can't apply the mean value theorem. So I am not guaranteed to have some number, i.e., I am not guaranteed some C for f prime of C equaling f of B minus f of A over B minus A. We have to stop there because that condition was violated. Okay, so there's one example. Let's do a second. Okay, I need to clear this. There we go. Okay. Next example. It's a common application, actually, of the mean value theorem. If a state patrol car sees a car from rest at an on-ramp in this given situation, he radios his partner 30 miles down the road, and that car that this original patrol car saw passes his partner 28 minutes later going 60 miles per hour. Okay. The officer gives the driver a ticket for exceeding the 60 mile per hour speed limit. And I want to use the mean value theorem to justify why the officer could give the driver a ticket. Okay, how could we think about this? First of all, are the conditions of the mean value theorem met? Conditions. It looks like we're measuring speed. Speed is distance versus time. So, or I could call it velocity. And I know that velocity is certainly a continuous function because I can't jump from 0 velocity to, say, 10 miles per hour in an instant. I have to have a gradual change. Even though it may be a fast change, the change has to be gradual. Velocity, so velocity is certainly a continuous function. And I could define it on a closed interval. Let's maybe say define on a time interval, because that's what we're given here. Let's say 0 minutes to 28 minutes. Okay, there's that. We've differentiated distance versus time functions, or excuse me, I should restate that. This is not a velocity function, this is a distance function, distance versus time function. I'll restate that. Distance is again a continuous function, but it's for the same reasoning that velocity is, because the distance that something travels, I can't jump from a distance of 0 to a distance of, say, 2 miles in an instant. I have to gradually, at least this car here has to gradually get there. And it's defined on a time interval from 0 to 28. It is differentiable. I know that its derivative is velocity. I know that the velocity exists everywhere because for every time between 0 to 28, I would be able to somehow give a set number for velocity for this car. It's differentiable. V of t exists on the interval 0 to 28. because at every instant in that time, the car has a velocity. The car has a certain velocity. So I could put a number to it. So the conditions are satisfied. Continuous, defined on a closed interval, and differentiable. Okay? So if I'm given that, how could the officer justify giving a ticket in this case? Well, if the conditions are satisfied, that means the conclusion is satisfied as well. So the conclusion states, and I'll note again here, my function f is a distance or position function, which I might call S of t. The conclusion states that for some time t, S prime of t, which is the velocity, I'll make a note here, this is velocity, I know that's the derivative of position function, is equal to S of, well, the time is 28, that final time, minus S of 0, divided by 28 minus 0. Well, I know what S of 28 is. The car traveled 30 miles. And S of 0, well, the car had not traveled anywhere from the original patrol car at that point in time. So we can call this distance 0 over 28 minus 0, which is equal to, let's see here, 30 over 28, but 30 is in miles, 28 is in minutes. So let's see, let's calculate that. Let me grab my calculator. $30 divided by 28 is equal to 1.07. Okay, so 30 over 28 is equal to 1.07, but that's in miles per minute. I need to change that to miles per hour. So this is 60 minutes in 1 hour, which is equal to 64.3 miles per hour. Okay, so that's the conclusion. What this means is at some time, some point in time, the driver, sometime I should probably specify, at some time between 0 and 28 minutes, we are guaranteed that the driver was going at that speed, going at about 64.3 miles per hour, which exceeds the speed limit in this case. We're told that the speed limit here is 60 miles per hour. So the mean value theorem justifies the ticket. Kind of a nice little application of that, unless you're the driver. Okay, that is all for this section. I think that I will stop this video and I will record more material on a new video.